Okay, so in this video, I'm going to go through some statistical problems. I've gathered like 11 questions. I feel that even though it's only 11 questions, that I cover a lot of ground and a lot of concepts in each one of the questions. So, with that being said, let's begin. Okay, so question one. So for a radioactive source with a repetitive count rate over a fixed amount of time, what distribution will the number of particles or photons follow? The answer is Poisson distribution. Now, if we have a large number of counts that are accumulated, what other distribution can we approximate it as? The answer is Gaussian distribution, or some people call it normal distribution. I prefer Gaussian. What shape do these distributions appear as? They are bell-shaped. So there they are sort of overlaying each other, bell-shaped. Okay, so in problems 2 and 3, in these questions, we're just going to go over like a quick calculation for Poisson, and then the next problem will be Gaussian. Okay, so Poisson first. Part A, what is the probability of getting a reading of 9 when the average reading is 10? There's the Poisson formula. Notice that there is a factorial along the denominator. So that could be a bit annoying. In this case, we're using 9 as the denominator. But, I mean, if the value was, let's say, 99, that would be a very, very, it would require a lot of work, essentially, to calculate that for the denominator. If you don't know what a factorial is, basically, let's say you have a factorial of 3. That means you go 1 times 2 times 3. Let's say it's a factorial of 9 in our case. 1 times 2 times 3 times 4 times 5, all the way up to 9. So if it was 99, you're going to do that 1 all the way to 99, multiply them. So let's work through this calculation here. So m is 10, n is 9. Let's plug the values in. And we'll work it out. And our answer is 12.5%. So in part B, let's perform the calculation, but with higher values. Same idea, plug it in, and we'll calculate it out. So a little bit higher factorial, again, 14. So the probability is 10.2%. Okay, so problem 3, we'll do the same question, but this time we'll use the Gaussian probability distribution. So this is the formula. Let's plug in the values. And I made the n match up appropriately, and I wrote down the variable. The average reading is the m. Okay, so let's plug in the values and work it out. So we get 12%. Let's do the same in part B, but with higher values. We get 10%. Okay, so so the point being, why do we care if the Poisson distribution, if we can approximate it as the Gaussian? The reasoning why is the factorials. So if we have some large value, even if I said 99 before, but what if we had 10,000? So that's why it's good to have. It's good to be able to approximate it with the Gaussian probability distribution. Now the other thing to note too is that so we're using smaller values here, 9 and 10, larger values here, 14 and 15. Our answers were 12% and 10%. 12% and 10%. Let's go back to problem 2 and compare. 12.5% with lower values. Oops. And 10.2% with higher. So with higher values, the distributions are closer. Okay, so problem 4. Okay, so in this problem, I just wanted to kind of start off with a couple like statements almost and kind of explain it a little bit. Okay, so let me go through problem 4. So as the number of measurements n goes to infinity, the expectation value is equal to the mean. Now, if you don't know what an expectation value is, or you forget, which is fine, I did put up a quick little calculation to remind you. And this is an example using a dice or a die, a six-sided die. So in the first part, we're calculating an expectation value. That is, you can roll the dice, you get 6 possibilities. So 1, 2, 3, 4, 5, 6. And you have a 1 in 6 chance of rolling each. So you get an answer of 3.5 for the expectation value of a dice. Okay, but what's the mean or the average? In this case, we roll the dice 10 times, we get our measurements, and then we divide by 10, we get an answer of 3. So I think if I just showed the definition, I don't actually think it would explain what the expectation value is. But with this example, I think it's pretty clear. Okay, so I just want to kind of show that because this statement has to hold. As the number of measurements goes to infinity, expectation value equals the mean. Okay, so questions. So what's the formula for the mean? It's right here. You add up the numbers, you divide by how many? The measurements. What's the formula for variance? It's equal to the mean. What's the formula for standard deviation? Square root the mean. What's the formula for standard deviation of the mean? It's square root the mean over the number of measurements. Okay, part E. What percent of readings will lie within one standard deviation in a bell curve? So it's 68.3%. What about what percent of the readings would lie within 2 standard deviations? The answer is 95.5%. And what about 3 standard deviations? 99.7%. So I would memorize, I don't think you have to memorize the Gaussian formula or the Poisson formula. That might be a little much. But I think, in this case, you should know these formulas. And you should, I think the average is probably intuitive. But memorize these formulas and also memorize what percent of the readings will lie within what standard deviation. Memorize these two. So here's a really nice depiction of the standard deviations with respect to the bell-shaped curve. And what I like too is, so it shows like one standard deviation is 68.3% within that area. So plus or minus 1 standard deviation, there's a 34.13%. Total, 68.3%. What I like here, though, is it also shows the percentile. So what about 2 standard deviations? 95.5%. So the 2 standard deviations goes from 2.3% to 97.7%. Would lie within that distribution. I like this depiction. Okay, so let's do some calculations. So if we measure a gamma ray for 10 measurements of equal duration, 100 seconds, the average number of gamma rays detected per measurement is 1 times 10 to the 5, this value. What is the mean count rate with the statement of its precision? So we're finding the standard deviation of the mean. So first thing, mean count rate. Mean count rate is equal to the mean divided by the time. This is the mean count rate. Now we need the standard deviation of the mean. So this is that formula again for standard deviation of the mean. It's the this is the average number of counts divided by how many measurements. So 10. In our case, we have 10 measurements. And we get our answer. But we got to factor in time. So divided by 100 seconds, and we get 1 count per second. So problem 6. Samples counted for 3 minutes produces 1,000 counts. The background is counted for 5 minutes and produces 400 counts. What is the net count rate? So we want to take the sample counted and subtract the background counted. So net count rate. So it's counts over time minus the background. And there's our value. What is the net count rate standard deviation? Take the square root of our answer for net count rate, and we have our answer. Okay, so questions regarding an error limits are actually pretty, you see quite a bit of them actually, which is interesting. So let's go through this question. So how many counts must be measured to obtain an error limit of 1% with a confidence interval of 95%? So I'll show you guys how to calculate an error limit. So notice that with a confidence interval of 95%, that means 2 standard deviations. Okay, so I'll show you how to calculate an error limit. I'll just show you the work-through. So basically, the answer is, so this is, first we're going to calculate the standard deviation. It's the square root of the number of counts, which is equal to 200. So this is a standard deviation. Now, to calculate an error rate, I'm going to take the standard deviation and divide it by how many counts. So I get 0.005. This is the error limit. But since we're using 2 standard deviations, we're going to multiply this by 2. So we get 1%. So the error limit is 1% in this case. Now, the question you're probably asking is, okay, wait, how did I calculate 40,000? And in this particular question, it's basically trial and error. So all I do is I would say, like, what's the square root of 10,000? 100. Okay, I would take 100 divided by 10,000. I get 0.01. Multiply it by 2. I get 0.02. Okay, it's got to be something higher than 10,000. Okay, I go to 20,000. And then I went to 40,000, and it was spot on. There are all kinds of different variations of this question that are commonly asked. So it's something to make sure you understand. A lot of the times, like, what they'll do is they'll give you the counts and they'll ask you to calculate the error limit. That's common. So make sure you kind of know the process. Okay, so problem 8. So the following set of count readings was made in a gamma ray field using a detector for repetitive time periods of 1 minute. So I have 1, 2, 3, 4, 5, 6. I have 10 count readings. Okay, so what is the mean value of the number of counts? The answer is 18,476. All I did was add them up and divide it by 10, because I'm just calculating the mean. Okay, so now we're going to get into an important concept, and that is that when we were calculating the standard deviation before, really what that is like the theoretical minimum standard deviation. You know, the distinction is this. You know, in the theoretical minimum standard deviation, they're only looking at like the aspects of the actual photons. They're not factoring in any precision with respect to like the instruments or anything of that nature, or any experimental aspects. So you have to almost distinguish. Do you want the experimental standard deviation or the theoretical minimum standard deviation? And I'll work through the problems and show you. So, okay, so part B is, what is the experimental standard deviation of a single reading? This is the actual standard deviation formula. I think you're probably familiar with it. You probably have it memorized. And this is what the actual experimental standard deviation is. So N is it's the mean value. which is this value we calculated. Ni is each value. Small n is the number of measurements in total. So in our case, it was 10 minus 1, so it would be 1 over 9. So all you essentially do is you put this in here minus the mean, square it, plus the next one in here, minus the mean, square it, plus the next one in here, minus the mean, square it. Add up all of those, multiply by 1 over 9, because it's 10 minus 1. And then I take it to the exponent 1/2, and this is my answer. Okay, part C. So what is the experimental standard deviation of the mean? So first I need my standard deviation. And then that formula from before, I take the experimental standard deviation divided by the square root of how many measurements, which was 10. Our value is 58. Okay, so part D. This is where, this is what we were actually calculating. It's the theoretical minimum of the standard deviation of a single reading. So what is it? All it is the square root of the mean, 136. And what's the theoretical minimum standard deviation of the mean? You take the standard deviation and then divide by the square root of how many measurements, which is 10. Okay, so problem 9. A group of patients exhibit lifetimes that are normally distributed with a mean of 36 months and a standard deviation of 3 months. What percentage of these patients will survive at least 42 months? Okay, so they give us the mean. We know one standard deviation is 3 months. So 2 standard deviations is 6 months, which would be 42 months. So we're essentially going by 2 standard deviations. Okay, but to answer this question, okay, yeah, so here we go. 36 months plus 6 months is 42 months. There's that 1 standard deviation is 3 months, 2 standard deviations is 6 months, and this is 95.5% falls within this distribution. But it wants to know what percent of these patients will survive at least 32 months. So the answer is 2.5%. And I'll show the diagram so you're clear what's going on. So remember the standard deviation, it would be 6 months on top of the mean, so this is 42 months. But remember that 95.5% falls in this distribution. It goes by, it's not 95% percentile, it's 95 as in going from 2.3% to 97.7%. So they're saying which will survive at least 2 standard deviations. You're setting the mark here. So the answer is only 2.5%. Okay, so just a couple quick questions on like statistics, p-value, and chi-square. And I'm not going to get into big detail in these, but I'm contemplating on making a problem series on that's only on these statistical quantities. It's like p-value, chi-square, and t-test, because you use them a lot in research. But this will just be a couple quick questions. So part A, what does the p-value mean? P-value is the probability of error in accepting the conclusion of the statistical analysis. What's chi-square test mean? It's a statistical test used to compare observed data with data we would expect to obtain according to a specific hypothesis. So just a quick question in C. If a result, 95% survival at 5 years, has a p-value of 0.01, what's the probability this was from chance? The answer is there is a probability of 1 in 100 that this result was obtained by chance. That's how p-values work, 1 in 100. Part D. If a chi-square test looking for a difference between two results claims of a difference with p-value of 0.01, what are the odds this result is correct? So what this is saying is that there's a 99% chance that this is true, essentially. Okay, last and final question is problem 11. Part A. What's the formula for measured counts in a non-parallelizable system? So this is the formula. R0 is observed counting rate. RT, true counting rate. T is the total time. So if this wasn't in rate, you would essentially divide this part by time. If it isn't with respect to rate, you don't need total time. Tau is the dead time. So this is just the same formula rearranged. True counting rate. This is observed counting rate. This is for non-parallelizable system. So what is the formula for a parallelizable system with respect to measured counts? This is the formula. Same quantities. R0 observed counting rate. RT true counting rate. E to the minus RT times the dead time. So the difference between a non-parallelizable and parallelizable is if you have a detection system that is within a dead time and a count occurs, like a radiation count occurs while it's in dead time, the non-parallelizable system just won't count that measured count, but a parallelizable system will actually restart the dead time again. So that's the difference if you're wondering. But let's do a couple quick questions. So for a system that measured a true count rate, 10,000 counts per second with a dead time of 10 times 10 to the negative 6 seconds, what's the observed non-parallelizable count rate? So we just plug it in the formula. What's the observed? We plug it in this formula. True count rate is 10,000 counts per second. Put that in. 1 plus true count rate times the dead time. We get a value of 9,090.91 counts per second. What's the observed parallelizable count rate? We just plug it in this formula. 10,000 e to the exponent minus 10,000 times the dead time, which is 10 times 10 to the negative 6 seconds. And we get our answer, 9,048.4 counts per second. So, I mean, it makes sense because the counts per second should be higher in the non-parallelizable as compared to the parallelizable count rate. So that's it for this video. I had 11 problems that I went through. Each of the problem, a lot of the problems are very, they cover quite a bit of interesting concepts, and I end up covering a lot of ground in only 11 problems. So I think that's it for this video. Thank you very much.